day, I'm Norman Wildberger. Today we're going to start exploring this reasonably interesting question of what happens when you divide one number by another, with the idea of trying to get some handle on how complicated a prime factorization ends up being once we have a couple of prime factors and we want to divide this big number by the prime factors that we have. All right, so it's sort of independent interest. What do you get when you divide one number by another in the decimal system? And to make it simple at first, we might just start with relatively simple fractions, like 1/2. So 1/2 we all know is 0.5. 1/3, well, that's already a little bit more complicated, because when we divide 1 by 3, it doesn't actually divide evenly in the decimal system. If we start doing a usual division, well, we end up with 0.3, and then we have to do it again, and then we get another 3 and another 3. And so there's a sort of sequence of 3s that we can keep on generating. So it's a process that in fact doesn't actually end. All right. So usually one says 0.333 and so on, but I'm going to put 2 dots here instead of 3, signifying that maybe we're not going to the end, but just a process that we could carry on and add more digits if we have time and patience. 1/4 is a lot simpler, that's 0.25. 1/5 is even simpler, that's 0.2. And 1/6, we're back in the same kind of situation here where we have some repetition, 0.16666, and it would keep on going with more 6s if we kept on churning away at the division algorithm. Now the more interesting thing happens once we get up to 7. At that point we see something that's a little bit more curious. That 1/7 is this famous looping sequence, 0.142857, and then it repeats 0.142857, 142857, 142857, as far as we're able to generate. 2/7 is a lot similar to this one. It's also a sort of cycle that repeats after 6, and in fact it's exactly the same numbers but in a slightly different order. So here it's 2, 8, 5, 7, 1, 4. So the same kind of numbers, but we're cycling through them starting from a different position. With 3/7 we get 0.428571. 4/7 it's 0.571428. And here's 5/7 and 6/7. So it's always the same 6 numbers, but you can think of them sort of as being on a circular track, always going in the same direction, and where you start determines the particular sequence that you're getting here. So a natural question is, well, what do these things actually mean when we write down something like this? What exactly are we talking about? Because it's not a standard decimal kind of number, as we've talked about in previous videos in this series. Okay, so make sure that we're all on the same page. So this 1/7, which is 0.142857, which we can think of as being the same sequence then repeated over and over again as far as we want to go, is generated by basically doing long division, of course. So we start with 1, and let's say we divide by 7 in the usual kind of way. Then at first we'd say, well, 1 can't fit any 7s in there, but if we go over to the second one, then we have a 10, and we can fit 1 7 in there. So we are usually a bit sloppy. We don't record where the decimal point is. Actually, there's sort of a decimal point that really goes all the way down here, and all these numbers really ought to have trailing zeros if we were really doing things officially correctly. All right, but the standard procedure, there's a 1 here, you get a 7, then you subtract the 10 minus 7 is a 3. And well, 7 does not go into 3, but then you can drop down the next one, which is gives you 30, and then you can see that 7 goes 4 times into 30. With a 28, then subtract, you get a 2, you drop down another 0, and then 2 times 7 will fit into 20, so that's 14 with a remainder of 6. Drop down a 0, get 60. How many 7s in 60? 8. 8 of them is 56. Subtract, you get 4. Drop down a 0, you have 40. How many 7s in 40? 5 of them. So 5 7s is 35, and then you get a remainder of 5. Drop down a 0 again. How many 7s in 50? 7 of them, giving 49, and then when you do one more subtraction, you're going to get a 1, which is just off the page here. All right, so you get a 1. And at this point, you're back where you started. You still can drop down another 0 and so on, but then the whole pattern is going to repeat. You're going to be in the same position as you were right up here. And that's the origin of the sequential or cyclical aspect of what we end up getting. So then everything repeats, and you can keep on going as much as you like. Okay, so because we like to actually see data in front of us, we don't mind doing some computations and then look to see what patterns we can find. Let's have a look at reciprocals of prime numbers. Starting with 1/2, which is 0.5. 1/3 we've already seen is 0.3 repeating. And we're using this bar over here to denote the repeating aspect. 1/5 is 0.2. 1/7 we've already seen. 1/11 is 0.09 repeating. So it goes 0.09, 09, 09, 09, and so on. 1/13 is 0.076923 repeating. So after that it becomes 0.76923 and so on. 1/17 we get a much longer cycle. 0.0588235294117647. With 1/19 we get another longish cycle, and 1/23 yet another one. Now if we count the number in these cycles, which is a very natural thing to do, well, here there's a cycle of length 6, here at length 2, here's another one of length 6. This one is 2, 4, 6, 8, 10, 12, 14, 16. Length 16. This one here is length 2, 4, 6, 8, 10, 12, 14, 16, 18. It's also one less than 19. And what about this one? The length is 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Again, one less than this. So there's a general kind of pattern that often it's one less than the actual prime. That's the length of the repeated cycle. But it certainly doesn't happen all the time, because if that was the case, then we would expect a cycle of length 12 there. We only get a cycle of length 6. So something is breaking down, but still there's a kind of an orientation, and we observe that this 6 is not equal to 12, but it's a divisor of 12. This 2 is not equal to 10, but it's a divisor of 10. And this 6 is what we would expect. And these ones here are kind of the exceptions, the primes 2 and 5. And that's of course because they're very special with regard to the decimal number system, because 10 is equal to 2 times 5. So those two particular primes have a very particular role in our number system. Okay, so there's something of a pattern here, but it's not entirely clear how to predict the length of a reciprocal of a prime, although we have a kind of an orientation as to how it might go, or what the major possibilities are. All right, so let's have a look at some more data. Obvious thing to do. So if we look at 1/29, which is the next prime, then we have this sequence here. That's all repeated, and its order is 28. We'll use this term order to represent the length of this cycle that repeats, all right? For 1/31, we get a cycle of length or order 15, which is indeed half of 30, which is ordinarily what we might expect. With 1/37, we get a very short cycle, just of length 3, so the order is 3, 0.027, 027, 027. And we note that 3 also divides 36. 1/41, we get this cycle, 0.02439 of order 5. And 1/43, we're getting this cycle here of length or order 21. So we are certainly moving towards this guess that in all cases, the order or the length of this cycle that appears when you take 1 over a prime divides p minus 1. It might be p minus 1, but if it's not, it's going to be a number that divides p minus 1. So another aspect of this question is, what happens when we divide not 1 by a prime, but say 2 by a prime or 3 by a prime? In the case of 1/7, 2/7, and so on, we saw that all the cycles were essentially just rotations of one sort of master cycle. What happens, say, with the denominator 13? Here's 1/13, which we've already seen. But 2/13 is a completely different cycle, but still of length 6. So So here we have 0.076923, and here we have 0.153846. And I've shown you the other fractions that you get by dividing various things by 13. And if you stare at this for a while, you'll see that they naturally fall into two different camps, which I've indicated by the color dots that are beside these numbers. So the red dots signify that we're always using these digits, but just rotated. So the digits 076923 in some order. So over here we have 230769. Over here we have 769230. Always the same 6 in the same order, but just rotated. And there are 1, 2, 3, 4, 5, 6 of those. So we're going through all the possible rotations of that basic cycle. And now the green ones, though, are going through rotations of this other cycle that's around, that's quite different from the first one. And there's 6 of those as well. So there's a pleasant kind of story here, but definitely we're in two different camps. There's two different sort of parallel things going on in terms of generating these decimal digits for reciprocals involving 13 in the denominator. Now, as you may have guessed from the title of this video, this whole phenomena of what kind of digits that we're getting in the cycles that occur is intimately connected actually with powers of 10, modulo the number that we're interested in. So it turns out that the decimal expansion of, say, 1 over n is intimately connected with the behavior of powers of 10 mod n. So our modular arithmetic actually helps us explain, at least partially, what's going on here. So to make it sort of obvious why there's a connection, let's have a look again at the 1 over 7 story. So here's the decimal expansion of 1 over 7, and I've repeated the usual long division over here. Okay, so if we look at the various steps that are occurring here, we can write them down in the following way. The first thing that we're doing is we're dividing 10 by 7, and we're getting 1 times 7, and then there's a remainder of 3. So we can represent that by this equation here. 10 is equal to 1 times 7 plus 3. That's sort of what's exactly going on here in this first step. Now at the next step, what we've done is we've taken 3 and we've added a 0, which is of course really the same as multiplying by 10. So notice that if we're working mod 7, so all of this is now going to be mod 7, that this thing here, 10 is equal to 1 times 7 plus 3. If we take 10 squared then, well, this is congruent to 0 mod 7, so it's just 30. And so we're multiplying this remainder by 10. It's the same thing that we're doing over here when we drop down to 0. And then at the next stage, we have to see how many 7s divide that. And there's 4 7s that appear there. 4 7s is 28, and a remainder of 2, and that's expressed in this equation. 30 is equal to 4 times 7 plus 2. And then the next step is represented by this equation. We multiply again by 10, because we're really taking this equation, it's really 10 cubed, which is 20, because this counts for 0 mod 7. And 20 is 2 times 7, that's the 14, plus a remainder of 6. And then at the next stage, 60 is 8 times 7, which is 56, plus a remainder of 4. And then we multiply by 10. 40 is equal to 5 times 7, plus a remainder of 5. And then 50 is equal to 7 times 7, plus a remainder of 1. And then at the next stage, we multiply by 10 again, and we get 10 to the 7 is equal to 10, or congruent to 10. And we're back to where we started. So I want you to observe that the remainders that we're getting here are just what the various powers of 10 are congruent to, or equal to, mod 7. So 10 is congruent to 3, 10 squared is congruent to 2, 10 cubed is congruent to 6, 10 to the 4th is congruent to 4, 10 to the 5th is congruent to 5, 10 to the 6th is congruent to 1. That's just, multiplying by 10 at each stage. But what we're doing here is a little bit more than what we did with the congruence or modular arithmetic story, because we're also taking into consideration what the quotients are. When we were doing modular arithmetic, The whole point was to ignore quotients and just focus on remainders. Whenever we had a quotient like this, at the next step we just threw it away and ignored it. But what we're seeing now is that the quotients that are appearing here do play a role. They end up just being these numbers up here. So this quotient 1, then the quotient 4, and then 2, and then 8, and then 5, and then 7. Those are exactly the digits that make up the number 1 over 7. So I think it's an attractive kind of story here that connects powers of 10 with the actual digits in the decimal expansion of 1 over 7. Now once we've made this connection between the digits of 1 over a prime and powers of 10 modulo that prime, then we can explain to a certain extent what's happening with the mod 13 case, the fact that we had these two camps appearing. When we looked at 1 over 13, we got this expansion here, 0.076923, all of that repeated. So here is a table of powers of 10 mod 13. This is part of a table that we've already had a look at in a previous video when we were looking at various powers, not just of 10, but of other numbers too, mod 13. So this is just one particular row. And we saw that no matter what number you choose, it doesn't have to be 10, it could be 9 or 8 or 7 or 2 or anything else really, that once you get to the 12th power, mod 13, you're necessarily going to get a 1. That's that Fermat theorem, that a to the p minus 1 is congruent to 1 mod p for a prime p. So there is necessarily a 1 there. But in this case, with the powers of 10, we see that a 1 also appears at the 6th spot, which is a divisor of the 12th spot. And it's that 1 appearing there which can be interpreted as telling us that there's going to be a cycle of length 6 rather than a cycle of length 12 as we might otherwise expect. Okay, and here are the various computations that you get, very parallel to mod 7 things that we just did. If we divide 1 by 13, well, at the first stage there'd be a 10, and that's 0 times 13 plus a remainder of 10. And then when we multiply by 10, and that would sort of bring down another 0 in our long division, then we would have 100. And that's 7 times 13 plus a remainder of 9. The remainder of 9 gets another 0, so basically we're multiplying by 10 again. That's essentially 10 cubed now. And that's going to be then 6 times 13, that's the quotient, and that's the new remainder of 12. And then multiply by 10, do the division, there's remainder of 3, multiply by 10, do the division, there's remainder of 4, multiply by 10, do the division, and finally we end up with a remainder of 1. And at this stage here, which is sort of the 6th stage, we're at 10 to the 6th, we then are going to repeat back, because if we multiply this by 10, we're going to be right back to here. The whole thing is going to repeat. So the repetition in the long division is basically a consequence of the fact that 10 to the 6th is congruent to 1. The fact that we're getting a 1 there means we're going to go back to the beginning, and that's where it cycles. What about the other camp, say represented by 2 over 13, where we get a quite different sequence of digits? Well, it's a similar story. We start with 20 now because we're dividing 2 by 13. So 2 does not divide, but if we take another power of 10, we get 20, and we can find some 13s in that. It's 1 times 13 plus a remainder of 7. And then multiplying by 10, 70 equals 5 times 13 plus 5. Multiply by 10, multiply by 10, multiply by 10. Finally, 80 equals 6 times 13 plus 2. And at that stage there, we're back to where we started. If we multiply by 2 again, we're back there. And the role of the quotients is just as before. It's telling us what the digits are. So there's a 1 times 13 here, a 5 times 13, and so on. These are the quotients that we get with these successive divisions, and they are forming exactly the sequence of digits in the expansion of 2 over 13. Just as over here, the quotient 0.76923 are forming the digits of 1 over 13. All right, so to summarize what we've sort of concluded is if we have a prime p And let's say it happens not to be either 2 or 5. These 2 or 5 are special. They're the primes that divide 10. Then Fermat's theorem says that 10 to the p minus 1 is going to be congruent to 1 mod p. That, in fact, requires p not to be 2 and 5. It's not going to be true if p is equal to 2 or 5. But otherwise, it will be true. This is telling us that you raise 10 to this particular power, and you're guaranteed to get something that's congruent to 1 mod p. Now, this may not be the only number that has that property. There may be smaller numbers that have that property. But if L is the smallest power with this property, that 10 to the L is congruent to 1 mod p, then first of all, this L should divide p minus 1. It should be a factor of p minus 1. And secondly, this is going to be the length of the repeating cycle for 1 over p. So in other words, let's say I gave you a huge prime, maybe 50 digits long, and I asked you, what is the length of the cycle that you get when you look at 1 over this prime p? Well, actually doing the long division might be very onerous. Okay, so now we understand a much more efficient way of thinking about what happens. It's really just a question of looking at powers of 10 modulo this prime. We know that if we take 10 to the 1 minus this prime, we're going to get 1 mod p. But we could also look at smaller numbers, which are divisors of p minus 1, and look to see whether 10 to any one of those is going to be congruent to 1. And if we find some of them, then the smallest one that we can find is going to end up being the length of this cycle. So that's a kind of an attractive story. We haven't really proven it entirely, but you've kind of maybe are convinced and kind of see how that's going to work. But a natural question is, what happens for a more general number, m, not necessarily a prime? So if m is another natural number, say bigger than 1, then we have to have a replacement for this. And we know what that replacement is. Okay, so that's Euler's generalization of Fermat's theorem. And I remind you that it's 10 to the phi of m is congruent to 1 mod m, where phi of m is Euler's totient function. And it's really the number of natural numbers between 1 and m, which are relatively prime to m. So the number of numbers less than m, which actually have no common factor with m. So if we're talking about, say, 6, then the numbers which are less than 6, which have no common factor with 6, are 1, not 2, not 3, not 4, 5, only 1 and 5. And that means that phi of 6 will be 2, because there are 2 such numbers less than 6, which are relatively prime to 6. And it's this replacement of Fermat's theorem which ends up allowing us to have a similar kind of statement as this, but for a more general m. So if we're looking for 1 over m and its decimal expansion, how long is that repeated cycle going to be? It's going to be having the same kind of relation to phi of m as this L has to p minus 1. In the case when m is a prime, then phi of m is actually equal to 1 less than the number. So in our next video, we're going to expand on this more general aspect of things and see what happens when we divide 1 or other numbers by not just primes, but more general numbers. And we'll actually go through some computations, even with some bigger examples, to see that we can actually get our hands pretty well on what's going on here by connecting with this modular arithmetic, which is very beautiful, and ultimately to Euler's insight into the very, very crucial importance of this particular number theoretic function. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.